Hi everyone, this is Kevamshi from adctt under the roll number having roll number 0407. So today I want to discuss about the signals and graphs from theory to applications under the subject analog and digital communication. Coming to the introduction part of this topic, uh, sampling is one of the fundamental techniques of a digital signal processing. In the sampling we convert the continuous time signal to the discrete time signal. It is a part of communication of signals. So the sampling of a time and a spatial domain signals in SS spaces is one of the most important building blocks of a digital signal processing systems. So sampling is a major thing where we use time signals, discrete time signals, and here the signals we need to process often have either types of connections and structures such as network signal described by graphs. So in this topic we describe the signals in the form of graphs, and GSP means graph signal processing has found numerous promising applications across many engineering disciplines, including many image processing, wireless communications, machine learning, and data mining. So graph signal processing is having the many applications using the sampling and many other methods in such a places where image processing and wireless communication, data mining, and etc. So on. So here you can see the generalized sampling in Hilbert spaces, where first picture depicts the sampling in Hilbert space, and second picture depicts the GSP counterparts. In the first part, we done the sampling transformation of a signal, and we constructed the correction transformation and reconstruction the transformation. Coming to the part B picture, we use the Hilbert space transformation of a signal, like generation of a signal and sampling of a signal, and same as picture A, like correction and reconstruction of a signal. So here GSP has found many problems as shown before. GSP has many applications like image processing, wireless communication, and machine learning and data mining. So an analog of a Whitaker-Shannon-Cordell sampling theorem is derived for functions with values in separate Hilbert space. The proof uses the concept of frames and frame operators Hilbert space. One of the consequences of this theorem is that it allows us to derive sampling theorem associated with boundary value problem and some homogeneous integral equation, which in turn gives us in generalization of another sampling theorem by Rabat. So these are the main thing. We use Hilbert space for the sampling of a graph signals, having certain conditions like boundary value problems and many theorems included in it. So here are some methods we use for the sampling of a signal, like vertex domain method. The below diagram depicts the original graph signal. As we discussed before, we represent the signals in the form of graphs. So here you can see the original graph signal, where we apply vertex domain sampling and we get the vertex domain sampled graph signal. So in the below picture, here we get the continuous, but in the below we get the discrete form of a vertex domain sampled signal. So also similar way, graph frequency domain sampling, it is also another type method where original discrete time signal method is done by time domain sampling, and we get the time domain sampling waveform. And you can see the DFT picture where discrete frequency time signal spectrum which defines the spectrum domain sampling. So as shown in above, here we done the sampling with the time as a parameter, but in the below we done the sampling using frequency domain. So sampling set collection and efficiently computation method. So along with signal reconstruction quality, computational complexity is another key concern when designing sampling algorithm, since signals may reside on very large graph. One would like to avoid computing the eigen decomposition of a chosen graph variation operator such as graph Laplacian, which requires large computation cost denoted by O of n3 in the general case. So we also provided an overview of fast and efficient sampling selection methods. As based on the some parameters like computational complexity, uh, we select the efficient sampling selection method. So here you can see the table which describes the different sampling method which are efficient in different parameters like maximizing the cutoff frequency, error covariance, approximate supermodularity, localizer operator, Newman series, uh, cumulative coherence, and global and local acceptability. So here you can see the determining random kernel function, localization in vertex domain, and localization in graph frequency domain, as we discussed before. So here another diagram which shows the community set of signals in the form of graph as a community graph, deterministic localization operator, random cumulative coherence, and Gaussian process, where we depict the original representation of these graphs. So coming to the application part of the graph signals, graph signal cross sampling has been used across a wide variety of applications such as wireless communication, data mining, and 3D imaging, and sensor placement, sampling for matrix computation, and subsampling of 3D point cloud. So these are the applications where we use the graph sampling processing or signals on graphs. So coming to the conclusion, the graph sampling framework is similar to sampling of standard signals. However, its realization is completely different due to the irregular nature of graph domain. Current methods have found several interesting applications, and interconnection between vertex and spectral representation of sampling, studies behind bilinear graph signals, and fast and distributed reconstruction of a graph signal. So I think get desired information. Thank you.